Hey y'all. So what we're gonna do here is just go through some basics of things that we should have learned in pre-calc, but um, didn't, just because of the school we're at and all that kind of stuff. So we're gonna talk about what parametric functions are, what polar functions are, and some vector representations. So we're starting with parametric curves. Basically, what parametric curves are is they're giving functions x of t, which is basically meaning x is defined as a function of t, meaning you'd have maybe like x equals t squared plus 1. And you also have y as a function of t, which means maybe you have like y equals, t, the square root of t plus 5, right? Just meaning like the x coordinate is defined as some other function, the y coordinate is defined as some other function. And you can plug in t values to figure out what the x and the y are, right? So we're just going to look at a couple examples of how to sketch a curve and then how to write the Cartesian equation, which is just the xy equation for it, right? So first one is talking about a particle is moving in the coordinate plane in such a way that x of t, right, there's our function with respect to t for x, and y of t is given by this one for t values between 0 and 5. If we want to sketch a curve for this, just like we would for any normal function, we're just going to create a table of values. So, except there's going to be t values, x values, and y values. Right? We want to go all the way to t equals 5, so we're going to plug in 0, 1, 2, 3, 4, and 5. And we have to plug them in two places, right? We have to plug them in for x, and we have to plug them in for y. And once we do that, we'll have an x and a y coordinate that we can graph. So let's go and start. Plug in 0 for x, for the x of t, and you're going to get 0 minus 5, which is negative 5. Plug in 0 for the y coordinate, and you're going to get pi over 1, sine of pi over 1, which is sine of pi, which is 0. So that's 0, which means we're starting there, right? At t equals 0, that's where the particle is. T equals 1, we have 2 minus 5, which is negative 3. And the y coordinate is pi over 2, which is 1. So this is going to give us 4 times 1, which is 4. So here we have negative 3, 4. 1, 2, 3, 4. That's there. Plug in 2, we're going to get negative 1. Plug in 2 there, we're going to get pi over 3. 4 times pi over 3. Sine of pi over 3. Sine of pi over 3 is root 3 over 2. Root 3 over 2 times 4 is 2 square roots of 3, which 2 square root of 3 is, let's see, 2 square root of 3 is about 3.4 something. So this is 3.4. So that's a little bit below that one. That's like there. And then plug in 3, and we're going to be getting 1 here. We're going to give me pi over 4, which is root 2 over 2, which is going to be 2 square roots of 2, which is about 2.8 something. So that's 1, 2.8 something. And then plug in 4, and we're going to get 3 for the x coordinate, and pi over 5, sine of pi over 5, which I don't know what that is, so I'm going to use a calculator. Sine of pi divided by 5 is 0.58 something times 4 is going to give us 2.3 something. So that's, we're going to 3 now, and 2.3 something, which is there. And then lastly, plug in 5, and we're going to get 5 here. And we're going to get pi over 6, which is 1/2, which is 2. So we get that. And so we could trace the curve. Looks something like this. And the cool thing is it says indicate the motion. We can actually tell which way the particle is going, which is cool. Right, so that's how you'd sketch it, right? You just do the x and the y piece individually. Example 2 is saying that we got a parametric curve defined by x equals 2 plus e to the t and y equals e to the 3t, and we want to find the Cartesian equation, which just means we want to write it in terms of y and x, no t, right? We want to eliminate the parameter, sometimes they would say. What this means is we need to solve one of the equations for t, right? So I think let's start with this one. Let's solve this one for t. So we're going to subtract 2 on both sides. And then we're going to natural log both sides, which is going to give us natural log x minus 2 equals t. So t equals natural log x minus 2. What we can do with that is we can plug it back into the other equation. So we have y equals e to the 3t. And we're going to replace the t with what t is equal to, which is ln x minus 2. And then simplify as much as we can. We can use the property exponents where any number on the outside can become an exponent. So this is going to be written as e to the ln x minus 2 to the third power. And then now that this e and this ln are next to each other, they actually cancel each other out. And we have y equals x minus 2 to the third power. Right? And that's the Cartesian equation for that curve. You could then graph it however you want. Some things to keep in mind as you do these, like sometimes, let's look for a third example real quick. Sometimes you might have something where x is determined, x is like sine t and y is like cosine t. To solve for t, you'd have to do like an arc sine or an arc cosine, but there is an easier way if you remember the let's write it this way. That's right. If you remember the sine squared t plus cosine squared t equals 1, if you remember that, then you can just directly plug in there, right? This would be x squared, right? Because x is sine t plus y squared equals 1. And so, you'd get an equation in terms of x and y a lot quicker if you did it that way, right? So that, like, this is something to remember that you can do. Okay, so that's that. Let's talk about polar equations. The thing about polar is you're going to have to remember a lot of trig identities and trig stuff. So let's write some of these things down. The basically what polar coordinates are is instead of locating a point by going some unit to the right or left and then some units up or down like like a map does or like the Cartesian coordinate plane does, in this coordinate system, you are given a radius away from the origin, how far are you from the origin, and an angle of rotation, like in which direction are you rotating. That's how you locate points. Here's some things that we need to remember, and I can explain this in a second. X equals r cosine theta, y equals r sine theta. R is equal to the square root of x squared plus y squared. That's just Pythagorean theorem. And then theta equals tan inverse of y over x. So these are some things that we're just going to have to remember. They all stem from, let's see where I can do this. Let's do this over here. They all stem from, if you think about any point in the Cartesian plane, like this point here, then the distance in the y-axis is y, the distance in the x direction, horizontal direction, is x. And then if we also try to relate this to what it would look like in polar coordinates, basically in polar coordinates you'd be given an r and a theta, right? The r would be this distance directly from the origin to the point, and the theta would be this angle here. And so we can create some relationships between this using just basic knowledge of trigonometry, right? So if you think about SOHCAHTOA, right, sine is opposite over hypotenuse. So we could say that sine theta equals opposite y over r. if you solve for y, right, multiply both sides by r, you get r sine theta equals y, which is that one that we had over here, right? You can do the same thing for cosine. Cosine of theta is adjacent x over r. Solve for the x, and you get x equals r cosine theta, right? The other one is just strictly Pythagorean theorem. This is a right triangle, so x squared plus y squared equals r squared. You take the square root of both sides and you get that. You don't need to consider the negative case because a distance has to be positive. And the last one where you get theta equals tan inverse is just the same idea as down here. Tangent of theta would give us opposite over adjacent. If we want to solve for tangent, we just have to tan inverse both sides, and that's how you would get this, right? So all those identities that are given there can pretty much easily be shown using just like some basic geometry stuff, right? So let's get into some questions that we might just be curious about. Like, start with this: convert r equals 4 sine theta to Cartesian coordinates, right? So like every single polar equation can be converted to Cartesian and vice versa. Sometimes it just takes a bit of work. So what do we have to do here is r equals 4 sine theta. We know that r is equal to the square root of x squared plus y squared. So instead of writing r, I could write the square root of x squared plus y squared. And then we know that theta, according to our things we have above here, we know that theta is equal to tan inverse of y over x, right? And so like already, we're kind of already done, except if you wanted to make it so it wasn't so disgusting looking, we would have to do some trig stuff to it, which let's do that. Okay, we can start with, let's just work with this right-hand side for a second, okay? So we're going to do 4 sine of, we're going to break tangent into what tangent is. Tan inverse is the same as sine inverse divided by cosine inverse, right? And then so basically what that means is we have sine of sine inverse over cosine inverse, which this first part is just going to turn into y. Okay, never mind. We don't want to do this. If you wrote that, erase it. That's a dumb thing to do. We don't need to do that. So this is what we got to do. Let's start on the inside, right? Let's try to evaluate this. Tan inverse of y over x. Think of what that means, right? Tan inverse of y over x means you're given this ratio, and it gives you the angle that produces the ratio, right? So tan inverse of y over x is going to give us 4 sine of that same angle that's there, right? That same angle that was used for the tangent one, which the sine of that angle is the opposite y over the hypotenuse. Sorry, the sine of that angle, there's no more sine here. The sine of that given angle is the y over the r. And then we can go back in and say the same thing we did on this right-hand side, the same thing we did on the left-hand side, which is that r is the square root of x squared plus y squared. Okay, and then we can multiply. Now we can try to solve, right? Multiply both sides by square root of x squared times y squared. On this side they cancel. Here on the left hand side we're just going to be left with x squared plus y squared because it's like squaring it, multiplying by itself. And on the right hand side we're left with 4y, which is I guess we're almost done, unless we had to write it in a better way. But I think let's call this good. We've converted it to Cartesian coordinates. We may not know what this is, but if you really wanted to know, you could write it like this, and then do what we call completing the square on the y piece, which means we're going to write this as y minus 2, where I'm getting 2 is its half of 4 squared, equals, basically when I'm doing this, I'm adding 4 on both sides, so there needs to be another 4 over here. And when you write it like this, it helps you see better what this is. This is a shifted circle. It's been shifted up 2 units. It has a radius of 2, right? So it looks like a circle that looks like this. Okay? Yeah, so let's go on to the next one. Let me pause it and erase some stuff here. Okay, so we're going to go in the other direction. We want the polar representation of this. Remember, we know that x equals r sine theta and y equals x equals r cosine theta and y equals r sine theta. So we're just going to replace our x with r cosine theta, and we're going to replace our y with r sine theta, like such. And then we can simplify this a bit, depending on what we're trying to get. Over 4 over 9. And then, because I guess like typically when we write these, we're going to write r equals f of theta. So it's like r, it's always going to be r isolated, just like we're used to with our Cartesian equations isolating y. So in this case, we're trying to isolate r in terms of theta. So we're trying to get r by itself here. So what we're going to do is we're going to go to multiply both sides by 4 times 9. So multiply by this and this to get them out of the denominator. Or what? That's probably confusing to you. So let's do this. Let's find a common denominator. Let's multiply this one by 9 and this one by 4. Right? So that's going to be 9r squared cosine theta over, not just 9 over 9 and 4 over 4. We're trying to find a common denominator over 36. And then this one over here is also going to have a denominator 36, but it's going to be 4r squared sine theta equals 1. We're trying to solve for r, so multiply both sides by 36. So you're going to get 9r squared cosine theta plus 4r squared, that's squared as well, sine squared theta equals 36. And then what you can do is both of these contain an r, so we can factor out they both contain an r squared, so we can factor that out. So we're going to write r squared over here, and then what's left is 9 cosine squared theta plus 4 r squared sine, oh no, there's no r left, we factored out the r, sine squared theta equals 36. And then you can divide both sides by this whole chunk, right? So we're going to divide both sides by that. And we're dividing on this side as well. So it's going to cancel out over here. And we're going to get r squared equals 36 over 9 cosine squared theta plus 4 sine squared theta. And if you really wanted to get it all by itself, then you could square root both sides to get something else. We can also simplify it a little bit. If you apply the Pythagorean identity down here to one of these, then sine squared theta becomes 1 minus cosine squared theta, which then becomes 4 minus 4 cosine squared theta. and there's a 9 cosine squared theta here. And so you would basically get 36 over 9 minus 4 cosines is 5 cosine squared thetas plus 4. And that would be maybe a simpler example or a simpler number. Some things to consider are what graphs look like. Just a second. So sorry, the video is still going. I thought I had it paused. Something to look at is what the graphs look like. So like Desmos has a really actually great way of doing this. The first one is just theta equals k, right? So the theta, if the think about it, if the angle is constant, then it doesn't matter what the radius is, right? So let me see if I can find theta on here. There it is. Theta equals 3, right? It doesn't like this. Why don't you like this? Okay, so let's talk about this first. If the radius is constant, then the radius is always 3, and you get a circle, right? Or if the radius is 5, you'd have a circle of radius 5, meaning the distance from the center to the edge is always 5. See if we can graph some of these other ones, like r equals 2a, r equals 2a sine, sine theta. Oops. OMG. And then a is some constant, right? So just make a like 5, right? That's a little bit big. 5, and you get this shifted up circle, right? It's like the same circle, but it's shifted up a little bit. If you made it 1, it'd look like that. Or you could do cosine theta. It was shifted. No, so notice 1 sine theta was shifted up on the y-axis because sine is like y. If you do cosine, hopefully you're thinking, oh, it's going to be shifted over like cosine. Or if I make it negative, then it's going to go over there, right? So I encourage you to actually go on Desmos and play around with these. You don't need me to do this on the video right in front of you and just bore you to death. So do graph these things on your own on Desmos and see what they look like. It's pretty cool. Okay, in example 1, it's asking us to classify each of the following equations according to the shape of its graph. So it's kind of like what we're doing here is just like thinking Cartesian. Like if you see y equals mx plus b, you're like, hey, that's a line. Or if you see like y equals x squared, you're like, hey, that's a parabola. Or if you see y equals e to the x, you're like, hey, that's the exponential curve, right? Or circles and all that stuff. So it's the same idea, just in polar. There's different names, different shapes, that kind of thing. So the first one we're trying to classify is r equals 5 plus 7 cosine theta. So we're looking for r equals some constant plus a number times cosine theta. And so there's 2 things to look at. This one kind of looks like it, except notice the difference here and here is that this one, the a is the same as a, and here you have 2 different numbers. So we just have to look, is 5 the same as 7? No, they're different. So this is I don't even know how to say this, limosone or something like that. We want to know, does it have a inner loop or an outer loop, right? So we have to determine if a over b is less than 1. So that's 5 over 7, which is less than 1. So a is a, let's just call it a lime cone. That sounds better. But it's not. It's limacone, I don't know, with inner loop. And again, I'm not going to do this on the video, but like really go onto Desmos and try it and see what it looks like, right? So you actually know what the heck is a limison, a lemon drink, whatever. B, r equals 4 divided by theta, right? So looking for one where you have a number divided by theta straight up. I can see it here. Looks like this. Oops, sorry, the one above that. That's going to be a spiral, right? This guy's a spiral. And then C is r equals 4 minus 4. So that's the one we were looking at before. These numbers are the same. So it's going to be a cardioid, which is like a heart-shaped thing. They're supposed to look like a heart. And again, please like graph them. I'm going to say it a million times, but graph them and see what they look like. Go to Desmos. It's fun. You can also do it in your calculator. But anyway. Next one is saying sketch the graph of r equals 3 cosine 2 theta. So when we're graphing in the polar, you basically have, let me do this in gray. These little circles, like this is when r is 1, this is when r is 2, this is when r is 3, this one is r is 4, and it goes out, right? And then the thetas, you can draw the thetas is like, oh, pi over 6, pi over 4, pi over 3, so on and so forth, right? So like the polar coordinate plane actually looks like a bunch of unit circles, or they're not unit circles anymore, but it looks like a bunch of circles with those special angles going out like such. We're being asked to graph r equals 3 cosine theta. And we can use some of this stuff about symmetry, which is right down here. Actually, no, we don't need to use that yet. Sorry. Let's just do with what we're doing here. R equals 3 cosine 2 theta. So we could just start plugging in numbers and see how this goes. It might take us a bit, but let's go ahead and do it. Let's just plug in some numbers. I'm gonna pause and plug in a bunch of numbers, and then you can check in with me, or we'll check in afterwards. Let's just set this up first, right? So theta is my independent variable. It's where I'm plugging things in. And then when I plug things in, I'll get an r out. So like example, if I plug in 0 for theta, it's going to be 3 cosine of 0, which is 3. So like when theta is 0 here, I should be on the 1, 2, 3rd circle out there, right? The next thing we'd probably plug in is like pi over 6, which cosine of 2 pi over 6 is cosine of pi over 3, which is 1/2, so this would be 3/2. So at pi over 6, it should be at 1.5, which is right in between 1 and 2, so like right there, right? And then if I plug in the next one, which is maybe pi over 4, we're going to get pi over 2, which turns out to be 0, so that puts us right there. And we can keep going in this fashion, and I'll do a few more. So the next one we get pi over 3, and then negative 3/2, which seems a bit funky, right? Like, how do I get a negative number here? Basically what that means is pi over 3 should be here, right? But we want to go the other direction from there. So like we're going to go this way, 3/2 instead, right? And which kind of gets funky. And so then if I plug in the next one, which is pi over 2, we're getting pi, which is 1, which puts us back at 3, negative 3 in this case. No, 3. Which puts us pi over 2, 3 puts us out here. And if you kept doing this, what you'd notice is you'd get these things that look like this, right? It looks like a rose or a flower. It looks pretty cool, but it's kind of tedious to have to graph the whole thing accurately. So what may be helpful later when we're trying to do derivatives and stuff is to know about some symmetry. So here's some examples. A polar curve will be symmetric about the polar or horizontal axis. So about like what we consider the y-axis, right? Or sorry, the x-axis. If f of theta equals f of negative theta. Basically what we're going to do here is we're going to plug in negative theta and see if we get the same thing out. It's parametric about the line theta equals pi over 2, which is the y-axis, the vertical axis. If f of theta equals f of pi minus theta, which again, we're just going to plug in pi minus theta and see if it's the same thing. And then symmetric about the pole or the origin, right? If when I plug in pi over theta, I get the same thing as I started with. So we're going to try to determine some symmetry of 2 plus 4 cosine theta. The way we're going to do this is we're going to start by trying if I plug in, we don't need to write this. If I plug in negative theta, do I get the same thing as I started with? So think about cosine of negative theta. So think about cosine of pi over 6 is root 3 over 2, right? What's cosine of negative pi over 6? Well, that's also root 3 over 2. So this one equals, right? You just think about things like cosine of pi over 3 is 1/2. Cosine of negative pi over 3 is also 1/2. The reason for this is if you think about the unit circle, you know, cosine is there and there. It doesn't matter, positive or negative angles, you're going to have the same x coordinate on there, right? So this one is symmetric about basically the horizontal axis. You can't say x-axis because there's no x's, so we call it the polar axis, right? We'd also want to check the other ones. Let me leave some space because it could have more than one symmetry. So we want to check the other one is, so we want to check is 2 plus 4 cosine pi minus theta equal to 2 minus 4 cosine theta, right? We're trying to check, we're basically asking this question, are they equal? No, this is supposed to be plus. So think about pi minus theta means, like, let's just choose a theta and see if it works, right? Let's just choose theta of 0. Is cosine of pi minus 0, which is cosine of pi, is that equal to cosine of theta? No, it's not, right? So this is not true, right? So there's no symmetry about pi over 2. And the last one we need to check is, does this equal, and I think, you know, just trying a number is going to be helpful at first. Try 0 again. Is cosine of pi the same as cosine of 0? No, right? So it's not going to work for this one. Next one is determine the type of symmetry again. So we're just going to check the things. Is 3 minus 3 sine negative theta, does that equal, right? So let's try some angles, right? Like, is sine of negative pi over 6 the same as sine of pi over 6? And if you think about the unit circle again, so here's sine of negative pi over 6 is negative 1/2. Here's sine of pi over 6, the y-coordinate is 1/2. So this is not true, right? And you can probably make some generalizations about sine and cosine here, right? Let's try, is 3 minus 3 sine pi minus theta equal to 3 minus 3 sine theta, right? If I subtract pi, so let's try 0 again. So is sine of pi equal to sine of 0, right? Because we're plugging in 0 for both of them. Yes, so let's try another one to make sure. Is sine of, let's try pi over 2. That's easy. Is sine of pi minus pi over 2, which is pi over 2, equal to sine of pi over 2? Yes. Let's try a slightly less obvious one. Let's try pi over 4. is sine of pi minus pi over 4, which is 3 pi over 4. The sine of 3 pi over 4 equal to sine of pi over 4. Sine of pi over 4 is root 2 over 2. Sine of 3 pi over 4 is also root 2 over 2. Yes, right? So this one is good. This one definitely works out. So it's symmetric about theta equals pi over 2, basically the y-axis, but you can't say y-axis. And then the other one, the last one we got to check is 3 minus 3 sine pi plus theta equal to 3 minus 3 sine theta. So we're adding theta this time. Let's try the basic ones again. Let's try 0. Is sine of pi equal to sine of 0? Yes. Is sine of, let's try pi over 2, right? Sine of pi plus pi over 2 is 3 pi over 2. Is that equal to sine of pi over 2? No, right? Because sine of 3 pi over 2 is negative 1. Sine of pi over 2 is positive 1. So this one is a no-no. And the same idea here. We're going to try all those things again. So knowing that it's cosine, I think the first one is a yes, so it's going to be a yes for about the polar axis. The next one we're going to do 5 cosine for pi minus theta, and we're trying to see, does that equal 5 cosine of 4 theta. So here we have to use some sort of trig identity. Let me figure out what it is. Okay, so basically, before we do this, this is going to turn into 4 pi minus 4 theta. The identity we're going to use is this one here, right? This is one of the sum angle formulas, so it's going to end up being 5 cosine 4 pi cosine 4 theta plus sine 4 pi sine 4 theta, which we're still trying to identify, does that equal the other one, which, oh, so, so cosine of, so this is going to be equal to 5. Cosine of 4 pi is the same as cosine of 2 pi, which is the same as cosine of 0, which is 1. So this is just 1 times cosine of 4 theta plus sine of 4 pi is 0. So this whole thing just turns into 0. So we're left with this, which is the same thing as the right-hand side, right? And so yes, they are equal. So yes, it's symmetric about theta equals pi over 2. And the last one we need to check is 5 cosine of 4. I'm going to go and multiply them right off the bat. 4 theta plus 4 pi. And we're trying to check, does this equal 5 cosine 4 theta. So again, we're going to use another trig identity. It's up there this time. It's going to be 5 times cosine of 4 theta cosine of 4 pi minus sine 4 theta minus times sine 4 pi. Again, this whole thing, sine of 4 pi is 0, so this whole thing goes away. Cosine of 4 pi is 1, so we're left with 5 cosine 4 theta, and we're left with the same thing. So yes, it's also symmetric about the origin. So it's all three symmetries apply. It'd be interesting to graph it and see what that looks like. Okay, so that's it for polar. The last thing we want to talk about is vectors. vectors are basically little rays, right? Like something like this, which represent a velocity and a direction, right? So the length of the vector, right, which is like the magnitude of the vector, tells us the velocity, and the basically like the angle that's going on with it is telling us the direction. The angle which it forms at the x-axis is the direction that it goes. So vectors can hold a lot of information in them, and kind of like they relate to parametric in that the horizontal and vertical components can be separated. The magnitude r, that r with the double absolute value, that's not what that means, but it kind of does, is the magnitude, right? So this is that means magnitude of r. So it's kind of, this is kind of a mix of like polar and parametric all at the same time. And if you want to know how to find the magnitude of r, it's basically just the Pythagorean theorem. And then if you want to know the direction, you can use tan theta equals y over x. Hopefully you're seeing how this is really similar to polar and a little bit of parametric as well, right? So we could also solve for theta using tan inverse. So let's look at some. Find the magnitude and direction of the vector represented by 6, 3. So I guess we should talk about first, what does it mean when they write 6 and -3 like that? And basically all it is kind of like a coordinate point, right? So we could graph this. Basically what it's telling us is that we're going to plot the point 6, -3, and that's our vector, right? So again, that the length of this piece is our magnitude, that which is like the r. And so to find that r, basically we're just going to use Pythagorean theorem, right? R is going to be, or like r squared would be 6 squared plus -3 squared, which we can solve by taking the square root of 36 plus 9, which is going to be the square root of 45, which is, we don't know what that is, right? It's not an obvious one. But we could simplify it to like maybe 45 is 9 times 5, so 3 square root of 5. All right, so the magnitude is 3 square root of 5. It tells us, like, the velocity it's going at. And then the direction. Oh, I messed this up. 6, -3 should be down here, right? Which is in the 4th quadrant. So don't think about it up here. But for the direction, we need to know the angle, the theta, right? So basically what we're going to do is we're going to say theta, right, is y over x, right? So we're going to do tan inverse of -3 over 6, which is -1/2. If you do this on your calculator, you're going to get -0.464. These are radians, which, is in the 4th quadrant, right? So that's giving us the direction. Okay, let's look at another example. Find the magnitude and direction of the vector represented by this. Again, what's happening here is basically we're plotting the point -5, -5, which is down here, right? And we're drawing a little arrow on it. And you can imagine there's like the x piece and there's the y piece. And then the distance, the hypotenuse of that triangle, is the magnitude. So it wants the magnitude first. So we're just going to do Pythagorean theorem. Each piece squared, so r is going to be the square root of 25 plus 25, which is 50, which is 25 times 2, right? So this is 5 square root of 2. That's our magnitude. And our direction is going to be theta equals I mean, we can tell already it's going to be in the third quadrant, right? So theta is going to be tan inverse. We can actually predict what it be. Notice how we went 5 to the right and 5 to the left. That's a 45-degree angle. It should be 5 pi over 4, right? Like it should be kind of maybe convincing here. So tan inverse, like this angle right here, is 5 pi over 4, right? So we're doing tan inverse of -5 over -5, which is 1. So we're trying to figure out what's tan inverse of 1. If you do it on a calculator, the calculator is going to give you pi over 4, right? Because the calculator is going to give you the one that's up here. So what we need to do to that, and this is something you need to think about, is we know that it shouldn't be up there, right? We know it should be in the third quadrant. So what we need to do to this is we just need to add pi, right? Like, so that's something you'll have to know how to do sometimes if you know it's in the wrong quadrant, but you know it's putting it in the wrong quadrant. You just add pi to it. Last one. Again, maybe it helps to sketch this. -1 root 3 means we go left 1 up root 3, right? So this would be 1 root 3, and that's r. If you want to know the magnitude, you take the square root of those things squared, which is going to be 3 plus 1. So the magnitude is going to be 2, right? So this is 2. And you want to know the direction, you're going to do tan inverse of y over x. So we're asking what's the angle that gives me root 3 over 1. -1, sorry, I should write this on here, -1, root 3 over -1. It actually is -pi over 3. However, -pi over 3 puts me down here, right? That's what it's going to give me, is down here. So again, I'm in the wrong quadrant. I can see that I'm in the wrong quadrant. So we just need to add pi, and that will give us 2 pi over 3. Right, add pi, it's going to put you there. So the direction is 2 pi over 3. All right, so that's what that is, and I'll give you some practice problems to do.